quite the beefy question we have here. We are given a building and we're told that, okay, we want to bring water to the 12th floor, which is located 16 meters above. And we're given some values here that the gauge pressure here, so an external pressure is being applied of 4.2 atmospheres. And there's the velocity of the fluid traveling through the pipe is 0.62 meters per second. And the diameter of the pipe is 5.4 centimeters at the bottom, but then tapers off to 3.0 centimeters at the top. Okay, so we are asked to find the velocity at the top and the gauge pressure at the top. Okay, so what really are we solving for in these? Well, here in this one, if we look at the overall Bernoulli's equation, which is the one we have to use to find out the pressures of the system here, we need to find, and we're given P1, but we need to find P2. Okay, what's the gauge pressure at the top? But we also have another unknown, the velocity final. Okay, how in the world do we go about this? Well, it's actually quite simple. We first need to not look at Bernoulli's equation, but the equation of continuity, that the area of a fluid initially times the velocity of it initially is equal to the final area times the final velocity. Okay, that initial idea, you've probably seen this before and done some calculations. We can actually go ahead and use this to solve for V final and then plug it into there and find our gauge pressure. Okay, can you kind of see how we will go about this problem? Okay, first of all, we need to find the areas. Assume the pipe is cylindrical, right? Who makes pipes in any other way? Square pipes? You ever see that? I haven't. So I know that the area of a cylinder or a cross-sectional part of a cylinder is a circle, and the area of a circle is equal to pi r squared. Hopefully you remember that from geometry or any other class you might have done. Maybe you're just learning it now, and that's wonderful, and that's all right. So let's find the respective areas for at the top and the bottom. So I'll go ahead and say area of the top is equal to pi r squared. So let's find the area at the top. We're given a diameter. A diameter is not a radius. It's 2 times the radius. So really, the radius here is equal to 1.5 centimeters. And this isn't in the right units that we want. We want meters, all right? Meters per second, that's gonna come in handy. Pascal, it uses the Newton, which is in meters, okay? So we really have to make sure that our values are in meters. So all we have to do to change this radius from centimeters to meters is just divide by 100 because there's 100 centimeters in every meter. So we divide it by 100 and we're gonna see that we get 0.015 meters. Okay, pretty simple. Let's do the same with this one here. I'm gonna follow the exact same process. I'm gonna divide it by 2, okay, and then I'm gonna go ahead and divide it by 100. So I get the radius of the pipe down here to be 0.027 meters. Okay, so we have the correct units. Now we need to find the respective areas. So for the area of the top pipe, let's do 0.015. Square that value, times it by pi. Okay, we're going to get the area here to be 7.07 times 10 to the negative 4 meters squared. Okay, and for the bottom, same thing. We will find that the area of the bottom pipe is, and let me just run the calculation, 0.027 meters. We're going to square that. We're going to see that the area is 2.29 times 10 to the negative 3 meters squared. Okay, so the area significantly shrinks at the top. That's important. That's that kind of allowing, squeezing a pipe will allow us to go faster. So we expect that the velocity final might be a little faster. So let's see. The initial velocity we're given is 0.62 meters a second. So we'll say 0.62 meters per second times the area initially, which is 2.29 times 10 to the negative 3 meters squared. I'm going to go ahead and remove this bottom part to make some room. Is going to be equal to the area at the top, 7.07 times 10 to the negative 4th meters squared, times that final velocity. Okay, so we're going to multiply these two together and then divide by here, and we'll get meters per second. Okay, that's just how the units cancel out. Times 2.29 times 10 to the negative third divided by 7.07 times 10 to the negative fourth. We're going to get that velocity final is equal to 2 meters a second. Nice whole round number, right? That's how we know we're doing this correct. If we get nice whole round numbers, because your teacher probably did that on purpose, and you know, why would she not make it 2 meters a second? So we'll write 2 meters a second for the velocity at the top. So it's coming in very slow, and it's going to be sucked up by the closing of the pipe. It's going to go whoop, and we're going to really have a high velocity when we get to the top. So I'm going to go ahead and erase all the work we have here because the Bernoulli's equation will get kind of messy, but notice I have here our simplified answer from all this work is 2 meters a second. So we have that idea, that our fluid is moving 2 meters a second at the very top, okay? Now we have to use Bernoulli's equation to find the gauge pressure at the very tippy top, right? We're given a lot of these values, but there is one thing we can cancel out, okay? And what would you think that is, right? If this is y equals 0 relative to our potential energy differential, okay, let's think about it. If the height is 0, what happens to this whole term here, right? Density is 1,000, gravity is 9.81, but the height is 0, right, relative to the system. So this actually all becomes 0, and it just cancels out, right? There's no potential energy at the very bottom. But as we increase our height, that value is going to be a non-zero. So the rest of it looks right, except for this. I forgot a square on my velocity final. What the hell's wrong with me? But everything else we have. We have a gauge pressure of 4.2 atmospheres. The molecules are moving with some kinetic energy based on the velocity of 0.62 meters a second. We have a gauge pressure at the top. We have a potential energy at the very top because its height is higher than where it started. And we have some velocity final at the end, or some kinetic energy final. So we can go ahead and do this, but notice one of our units is wrong, and that's the atmospheres. Atmospheres are not in Newton, or the newtons over meters squared, right? We need to have that in a different form. That's where this conversion comes in handy. One atmosphere is 101,325 pascals. So I'm going to go ahead and just convert this quick. And remember that a pascal is a newton over meters squared. All right, we'll write a pascal as that. If you're not aware, now you are. A pascal unit is equal to a newton over meter squared. Okay, so let's get right into it. 4.2 divided by, right, because we're going to do a little bit of dimensional analysis where 1 ATM is 101,325 pascals, right? We're going to multiply it by that number. And we're going to see that instead of 4.2 atmospheres, we have 425,565 pascals, and we'll simplify that to the newton over meter squared. Okay, so we have everything we need in the correct units, thank God. Now let's solve for that gauge pressure. So this is what we're solving for. Let's do a little bit of rearrangement of the Bernoulli's equation to help us solve for just P2, so this calculation goes by a little quicker. We'll say that P1 plus 1/2, and this is the kinetic energy of the fluid, squared. And then we're going to subtract over not only the potential energy, but the kinetic energy term as well, right? So this will be equal to, and let's see, that potential energy minus the 1/2 of the, or not the 1/2, but the kinetic energy term on the final side. So if we were to plug in every single variable, we'd get P2. Okay, so let's do that. Why don't we? We're going to say that the gauge pressure at the top is equal to, and let's bring in our first term as a pressure. We're going to add that to the pressure from our kinetic energy, so 1/2 1/2 pressure. So we know the pressure, the density of water to be 1,000 kilograms per cubic meter. We know the initial velocity was 0.62 squared, right? So we are going to get that the pressure due to kinetic energy is 192 pascals or Newton meters squared. Right, so that's a very, very small term and not likely to contribute much, but it's still important that we keep it there. I'm actually going to go ahead and combine the two terms just to keep things simple. 565 plus 192, and we will just simply add over that amount since it's so small. Okay, so we have that term. Now we need to subtract it by this term here. So what is our density, gravity, height final? So we know 1,000 times 9.81 times the height final, which is 16 meters. We are going to get 15,6960 newtons over meters squared. Okay, and then we need to subtract that by the pressure due to kinetic energy, which is 1/2 times the 1,000 kilograms per cubic meter for the density, and then we need to times that by the final velocity, which we found to be 2 meters a second, right? So we square that and we get 2,000 Newton over meter squared. Okay, now let's just do some simplification, subtract this by all of this. So the 425,757 newtons per square meter minus 156,960 minus 2,000. We're going to find that the final gauge pressure is 266,797 newtons per square meter. Okay, so that's the gauge pressure. Now what we need to do is convert this to atmospheres, because we were given an atmosphere here, right? In atmospheres, 4.2. So we should probably give our answer in atmospheres. So all we have to do is divide by this conversion factor, right? Because pascals would be on the bottom over atmospheres, right? And we want to get atmospheres. Pretty simple idea. So let's just divide 101,325. We're going to get that our final pressure is equal to 2.63 atmospheres. So that's the pressure at the top. The gauge pressure at the bottom, it was like 4.2 something. Now it's only 2.63. Hope you guys enjoyed this episode. If you did, please drop a like and subscribe. I greatly appreciate you watching this video and my very, very long explanation for it. Have a wonderful day.